Okay, welcome to CULINOLOGY 101 week 8 content. Okay, so for this week, the week 8, we will be learning about the physical quantification and changes of food method. Okay, so all these few weeks is going to be quite fundamental, which means that these information they are very important in terms of for product development, because we will need to do unit conversions. Okay, so you need to build a strong foundation in terms of calculations, density, unit conversions. Okay, all these are very crucial, and understanding about changes of matter from solid to liquid to vapor, okay, or gaseous state, and back forth. Okay, and how the pressure influence these changes are very crucial, okay, and fundamental. Okay, so let's look at the learning objectives. There are 5 objectives: able to recognize, use, and convert various measurement units, able to calculate the density of matters. Okay, you will have a tutorial on that. Okay, tutorial question on that to practice. Forces affecting the states of matter, physical properties of different state of matter, changes between different state of matter. Okay, so let's look at the first one, which is the measurement units and unit conversion. Very crucial, because you will need to do it correctly. Although you may think that I have learned before, but do you actually still remember, or are you good enough, okay, to do the conversion? Okay, very critical. Okay, so how do we measure? Okay, so how do we measure the just a bit. So in the lab, when we want to measure the mass, okay, or weight, we will use a weight balance machine. Okay, very important. Yeah, if you are doing any weight balance machine, usually at the one corner here there's a bubble. Okay, there's a bubble where is showing whether the balance machine is sort of like is even between the different type of different angle. Okay, so you need to make sure for the bubble, right, usually is like that. Yeah, so you will see over here, okay, 2 line, then they will have a bubble. If the bubble is here, you need to adjust the leg into the middle here. Okay, usually there's one corner, okay, or 2 corners, right, that is adjustable. Okay, there's 1 or 2 corner adjustable, so you need to slowly adjust to make the bubble into the middle. Usually this one you need to have a practice. When you first go or second go, right, you take some time to adjust that bubble to the middle, but once you are fluent with that, then you're okay. Although not much difference, okay, but the accuracy is there. Okay, so before you do any balance, make sure that the bubble is in the middle. Yeah. And then secondly is that after you balance it, okay, after you check the bubble is in the middle, okay, then after that you will need to zero it. Then after that only you put your items on top to measure. Secondly is very important, right, is that make sure the area, okay, the area where there is a weight the balance machine, there's no external factor affecting the measurement. Okay, these external measurement including vibration, okay, from the table, and also air, okay, like aircon blowing from top to bottom, it can affect the numbers. Yeah, so a lot of times in the lab, students will say, sir, there's something wrong. The balancing machine the numbers seem to be jumping up and down. Okay, then I check, then I say, okay, then I look at up there, the aircon is full blowing. Okay, then I say, can you go and switch off the aircon? Okay, and I say, oh, the number no longer jump up and down. So very simple. Just off the aircon for a while. Okay, then after that, after finish the measurement, then turn back on the aircon, problem solved. Okay, so these are few things that you need to remember, okay, when measuring the mass, yeah, or weight. Of course, you need to check the decimal place as well. How sensitive is it? There are different weighing machine, okay. Some, if it's like 0.000 grams, which means that you can measure down to milligram, okay, the sensitivity. If it's here is 0.0, don't use it to measure milligram, use it to measure grams, alright. The second one is volume. The best, the most accurate measuring volume is using a volumetric flask, okay, because you see over here there's a line here, okay. This line is different from volumetric flask to volumetric flask, which means that even though here written 1000 ml, but this line is different because each of these flasks is individually calibrated. That's why this line will be slightly higher or lower depending on the calibration, okay. So if you want to measure, the most accurate is using a volumetric flask. So what you do is that you measure, you make up the solution, at the end only top out to the line. Very important. Don't top out all the way to the line first, because sometimes the whatever you add inside, right, will increase the volume, okay. You may say, sir, how about the measuring cylinder? Okay, it's okay. You if it's not, you don't require that accurate, you can use the measuring cylinder. But how about the beaker? Beaker sometimes got right there 100 ml. Do not use that. Beaker, okay, conical flask, the measurement over there like 100 ml is very inaccurate, okay. Volumetric flask is still okay, okay. The best is the measuring cylinder is still okay. The best is volumetric flask. Thermometer, you got this or infrared, okay. For this, with the sharp one, you can poke inside and measure the internal temperature. Very important in terms of food product sealment, okay, because you need to measure the internal temperature. Okay, and another popular one is the infrared. Okay, it's like a gun like that, the infrared. You can use that as well. It looks very cool and it's very expensive, but the problem is that the infrared cannot penetrate into the meat, okay, or your product. So you cannot measure the internal temperature, but it's very cool. Some people, they will use it to measure it, okay, the temperature. Okay, so a old school, a conventional one, thermometer like this is good enough, yeah. Then you got calorimeters, okay, similar to that you can use it to measure the calories, okay. Okay, how do we measure in labs? Another thing is that is very often is using just rulers. Okay, to be honest, a lot of the measurements for your product development using a ruler is one of the very standard one. Okay, so a ruler, okay, there's you need to actually put it properly, okay, to measure the heights. Some people, they will, for example, they will use it to compare the different heights of the breads, okay, after they improve the recipe. So the one of the things that you can use it to prove is using the height. So you just place directly or perpendicular or with the table, put with the bread, and then you can measure. Maybe the first one is like that, second recipe is like that, third recipe is like that. Okay, so very important, you do not take artistically for the photograph, say, oh, one angle is nicer than the other angle. You take picture straight, place the ruler perpendicular to the table and put your product side to side, okay, with the visible of the numbers over here. Very simple type of measurement, but very crucial in the case of product development. Just measure the height of the product, how much it rises. Okay, sometimes because of the rises, it actually translate to the amount of the air is in there, the air pockets in there, translate to a different type of texture. Okay, so some of the commonly used units, okay, so we have here like volume, liters, milliliters, okay, cubic centimeters, length. Okay, usually in the kitchen you'll use like meter to centimeters, sometimes millimeters, depending on what you are working on. Calories, kilocalories, there's the common one that you use. Celsius, okay, the one that you use quite frequently, okay, in Malaysia. Kilograms, grams, milligrams, yeah. So these are the way of convert the units, okay. So if you want to convert from the milliliter to centimeters, okay, so you just multiply by another 10, okay. If you want to go to microyard, multiply by another 1000 and so forth, okay. So all this conversion, I would expect you to know how to do the conversions. In the tutorial question, they will have a number of questions for you to just to play around with it to get yourself more familiar. Make sure you know how to convert and fast, okay? Why convert between units? Okay, because you are dealing with different type of the stages of the product elements, okay? So very simple example, when you are doing R&D in the R&D kitchens, okay, doing prototypes, you are only doing in a very small lab scale, okay. Once your recipe is ready, then you will up your scale to what we call the pilot scale, much larger, okay, from milliliter now to liter, okay. So at first you are working with milliliter, okay. Then when you upgrade, once your recipe is finalized, okay, you want to increase to a larger volume, what we call a pilot trial. So usually is in the liter, maybe it's 10 liter, 20 liter, 30 liter, okay, small batch. Then once you confirm it's workable, only you translate that into a production, okay, and that will involve tons. So you do not, so you must know how to convert from a small volume to a large volume, okay. So if you do if you convert wrongly, what happened? Your recipe all gone. Your recipe is out, and your product is out as well, and you waste a lot of money. Okay, so unit conversion is very, very important. Okay, if you're looking at some of the factory, okay, how factory measure the weights? Usually they is come by a truck with a container. So when the empty container comes in with the truck, they actually will go to a giant weighing machine and measure the weight of the empty container and the truck. Okay, once loaded, they will go back to the weighing machine and measure again. So now with the load, so the weights with the container, the loads and the truck minus the initial one, which is just truck and the empty container, will translate to the product weight. This product weight very important for to checking what is out from the factory and what is in of the factory. Okay, very important. Okay, unit conversion, very simple question. Calculate the area of rectangle that has a side of 1.5 and 2. The area is very simple. This one side multiplied by the other side, and the unit will be meter square. Okay, so there you go, 3 meters square. Okay, the area, very simple. All measurement in international track and field events are made using metric system. Metric is like kg and so forth. Yeah. Javelin throw by female competitor must have a mass of no less than 600 grams. Express this mass in kilogram and milligram. Very simple. From gram to kilograms divided by 1000. So become what? 0.6 kilogram. If you want to change it to milligram times 1000. So become 600,000 milligrams. Okay, very simple, right? A level transition using a micropipette. Okay, so micropipette is another skill that you will be learning, yeah, when you're back to the lab. Okay, micropipette is just a small pipettes. The skill of using it, the theory is very simple. Just press, load, okay, go to your substance and then press it down to unload. Very simple, the theory. But the accuracy, okay, the accuracy is very, very depending on the skill. Okay, to make sure that if you are loading 50 milligram, okay, or maybe 50 microliter, it's 50 microliter, not 51 microliter or not 49 microliter. Okay, the skill is very important. But don't worry, when go back to lab, I will teach you, okay, how to use a micropipette with high accuracy. Okay, so a lab technician uses a micropipette to measure a 50 microliter sample of blood serum for analysis. Express the sample volume in liter. Wow, from microliter to liter, that's a very, very big difference here. So what you do is you divide it by about by 1000 and 1000. Okay, so you can see is you need to divide it by 1 times 10 to the power of 6. So we change to a liter, so it turns out to be 5 point times 10 to the power of negative 5. So it's divide, yeah, divide. So you go behind, so it will be 0.00005, okay, liter. So you do not express 0.00005 liter. You can express like that, which is more easier to see, yeah. So it's 5 times 10 to the negative 5 liter, yeah. How about this, changing jelly beans? Okay, so you got empty jar, you fill out the jelly beans. So now you want to see what is the jelly beans, so you take the number divided by the empty jar and the empty jar. Okay, so this minus this, you will see that it's roughly about 181 grams, okay, of the jelly beans. Very easy. Okay, so this is very similar to the truck concept that I gave you just now, yeah. Okay, the next is, after unit concept, is learn about density, yeah, of matter. Okay, let's look at the density of matter. So the density of matter, right, is you're looking at the specific volume, which means that within this specific set of volume, how much mass is in this volume. Okay, so that is what we call density. High density means that within this volume, the mass inside of the atoms or the molecules is very, very high. Okay, it's very rare. It's what we call dense. Okay, if it's dense, means that the mass inside is very, very packed. Okay, or very, very high within this set of volume. Low means that the mass very little within this set of volume, yeah. So density also is closely related to the state as well. Okay, usually gaseous state is very low density. Okay, liquid is slightly higher, and the highest is actually solid. But if you're comparing solid and solid, different metals, they have different density as well. Some of the solids is higher density, some solids are lower density. Okay, so it really depends, yeah. If you're looking at this is a classic example, the density of oil versus water. You will see that the oil will always float on top of water. You might be thinking, why is that? Okay, if you check the density, the oil has always lower density compared to water. Okay, you have to compare within the same temperature, yeah. In other words, the oil is lighter compared to water. Water is heavier compared to the oil. That's why the oil is always floats on top. Okay, so some very simple calculations. Again, more calculation can be practiced in the tutorial question. Please try it. Okay, it's slightly more challenging. Okay, so the density of iron metal has been determined to be 7.2 grams per cm cube. Okay, so this is volume. Cm cube is a volume, so grams per volume. So this one is the density. Use this value, the density value, to calculate the mass of iron sample that has a volume of 35 cm cube. So very simple. You just multiply this number with this, you will get the gram. Okay. Use the density value to calculate the volume occupied by 138 grams of iron. Okay, so if you want to look at the volume, okay, in cm cube, then directly this number divided by 7.2 grams. Okay, so you can see the calculus here. Okay, so you get that, yeah. Yeah, you will see that later on, yeah. Okay, the next one is we're going to learn about the forces affecting the state of matter. Okay, you will use the kinetic molecular theories, okay, potential energy and kinetic energy, to explain the property of matter in different states. The different state we are going to talk about is the solid state, liquid state, and the gaseous state, yeah. Because whenever you are playing with the formulation, or cooking conditions or cooking processes, you always play around these few states, yeah. Okay, do calculation based on the specific heat of matters, and do calculation based on the combined gas law, okay, Dalton law, Graham laws, and ideal laws, yeah. Okay, looking at these forces affecting the matters, when you want to look at the forces affecting matters, the matters that we talk about, okay, so matters can exist in three different states, yeah, solid, liquid, and gas. Usually, you will see that it's in the set temperature, okay. Whether it's existed in solid, liquid, or gaseous, usually you need to fix at a certain the temperature, yeah. Okay, if just say you're talking about room temperature theoretically is about 24, 25 degrees Celsius, okay. So in that state, okay, because temperature is an energy will affect the intermolecular force, okay. We have spoke about that in the organic chem before, yeah. So when you're looking at that, the matter can exist in three different states: solid, liquid, or gas. If you're talking at room temperature, you're talking at colder temperature like 5 degrees Celsius, okay. You're talking about like warmer, 40 degrees Celsius, you talk about 40 degrees Celsius, okay. So it's really depending on the state, okay, the temperature it is in, alright. Okay, so what affects the state of matter is the forces acting within intramolecular force and between the intermolecular forces, molecule or ionic compound affecting their state of matters, yeah. But usually is the intermolecular forces, the force between the molecules, okay, how strong it is. If it's strong, usually is the solid state at the temperature, yeah. At the fixed temperature, if it's strong, then it's in the solid state. If it's slightly weaker, in liquid state, because they can move around. If it's very weak, they can move very far apart, it's a gaseous state, yeah. So usually it's related to their intermolecular force. So an element or compound can be made of atoms joined together by intramolecular force like ionic bonding and covalent bondings. Okay, we have learned that in organic chemistry. Okay, molecules can interact with each other through intermolecular force like hydrogen bonding, dipole-dipole forces, dispersion forces. We have learned that also in organic chemistry. Okay, so what happened, right, is that there are two forces, cohesive force and disruptive force. Okay, so cohesive force is how attract are the forces between the particles. Disruptive is to pull them apart. Okay, cohesive and disruptive. Okay, cohesive force is the attraction force acting between the particles and is associated with the potential energy. Yeah. Okay, potential energy is the energy a particle has a result of attractive or repulsive force acting within it. Okay, so this one is very familiar. You have seen that in organic chemistry. So when you're talking about a certain molecule, okay, this is talking about intramolecular force. Yeah, you can use this to explain about intermolecular force as well. Okay, so looking at this potential energy curve, usually when they are far apart, there's a attractive force until an optimal where they form a bond. Okay, until they form a bond at a certain distance. Okay, this is the most stable and they will fix there. But when they get too close, it becomes a repulsive force. Okay, Later on, this kind of theory we also will apply to emulsions. Okay, they will attract, but what happens is that when they have a certain length, they will associate, but when they have too much force, they go too close, they will repel. Okay, later this kind of theory will also apply to emulsion droplets. Yeah, this one is later on lah. Okay, other chapters. Yeah. Okay, so you can see from here, there's an increased strength. Okay, there's an increased strength. Here is more difficult to pull apart. This one is easier. That's why usually when you're talking about the change of state of matter, you are changing, you are affecting the intermolecular force. Okay, not so much of the intramolecular force. You affect the intermolecular force. Yeah, usually molecules. So the disruptive force tend to scatter particles and make them independent of each other. So you are trying to pull them apart. Disruptive force is to pull them apart. Yeah. So you look at the when you're talking about particles, right? Usually they are in a constant motion. Okay. The kinetic energy between particles increases with temperature. That's why early on I say that the temperature is very important. So you cannot compare one molecule at cold temperature like 5 degrees compared to another one at room temperature 24. You need to compare at the same temperature, yeah, because temperature is an energy. Increasing temperature, you increase the energy that available between the molecules. Okay, so what happens is that when you increase the temperature, okay, when you increase the temperature, then what happens is that they have more energy, and this energy will break them apart. Okay, we separate them or separate them, not break them, we separate them apart. Yeah, especially when you talk about intermolecular force. So you are talking really about the state of matter. You are talking about the balance between the cohesive, attracting, and disruptive force. Okay. The solid state is where the cohesive force are stronger than disruptive. Okay, that's why more or less they have a fixed position. Okay, although they are vibrating, but more or less they are vibrating within the space. Okay, not really that much. Okay, fixed position vibration. Okay, until you give enough energy for them to, so much energy until they separate each other. Yeah. If enough of energy, then they will separate. That is when the the disruptive force slightly increase. Okay, but still cohesive force still slightly dominated, still dominant. Okay, still dominate. So cohesive force still trying to pull them together. Okay, and so with that, they tend to like very near to the molecule itself. Although they can slide past each other, but they are very close to each other. Okay, they are sliding each other. Okay, particles are randomly packed and relatively close to each other. Yeah, they are sliding freely one over one another without sufficient kinetic to be separated completely. Separate completely when they have a lot of energy. Okay, that is when the disruptive force are dominated. Okay, compared to cohesive. That is when they separate and then the particle will move in the straight line. Okay, and then move at a straight line until they bounce, and then they will bounce away each other. Okay, so gaseous state is that. Yeah. Okay, changing from state to state also, there is one stage where you see that they didn't change any they didn't change the what we call the stage. Okay, that is when they increase. Okay, the temperature, you can see from here, the temperature increases and then they will stop for a while. Okay, the temperature didn't increase. All right, that is when they absorb a lot of energy to change to the next phase. Okay, again, they absorb energy before they change to the next phase. Yeah, so you will observe that as well. Okay, you observe that, how come the temperature is not changing? Okay, all right, it's because it's absorbing the heat, okay, before it change. All right. Okay, let's look at the physical property of different state of matters. Yeah, very simple. The physical property we talk about in this is the density, the shape, the compressibility, and thermal expansion. Okay, how much it can expand due to the the heat. Yeah, the density, if you compare, right? Okay, solid density is very high, liquid is high but usually lower than the solid, gaseous is low. Okay, the density. Okay, again, density, you're talking about how much molecules are in the set volume of the yeah. The shape, solid usually cannot fix, is fixed. Okay, so you cannot change. Liquid, it depending on the container. Gaseous, it can take the shape of the container. Yeah, so you see over here, yeah, solid, liquid, the shape of the, okay. Compressibility, okay, how much you can compress. Solid, not you can't really compress much, okay, because it's very high density already. Liquid, you can compress, okay, you can compress, but usually is slightly harder to compress, yeah, because you can compress, but it takes a lot of efforts to compress. Gas, you can compress much more easier, yeah. But again, yeah, just to reiterate, sometimes using pressure to compress, you can change from one state to another state. Yeah, like gas state, if you compress more, you can become liquid. That is why you got liquid nitrogen, because the nitrogen gas is being compressed so much, it changed to a liquid form. Okay, so that is due to you pressurize it a lot. Okay, change from one state to another state through pressure. Okay, thermal expansions. Okay, how much you can expand due to the increase in temperature. Solid, very small. Liquid, small. But gas, moderate. Yeah, okay, so which means that you give slightly more the temperature. Okay, slightly increase the temperature, the gaseous will expand more, okay, in terms of the volume. Changes between different state of matters. Okay, looking at this, what factors change the state of matters? Matter can change from one state to another by heating, cooling, or changing pressure. Like the liquid nitrogen example I gave you is the changing pressure. Okay, where you pressurize the nitrogen gas, you can actually change from a gaseous state of nitrogen to a liquid nitrogen. Okay, so liquid nitrogen, you can see that nowadays is quite popular. They use it to make ice cream, liquid nitrogen ice cream, right? So this is the changes of state of matters. Okay, so what we have is from solid, if you change to liquid, is called melting. Liquid to gaseous is called evaporation. Yeah, if you change directly from solid to gas, is what we call sublimations. Okay, one of the very special, or usual, not special, I mean as in common example is the changing of carbon dioxide. Okay, the what I call dry ice, it can directly supplement to change to gaseous state. Okay, that is the dry ice. Okay, or the solid form of the carbon dioxide. Okay, you change from a solid to gaseous state. Yeah, they will skip the liquid state. That's why if you are using the liquid nitrogen, okay, or dry ice, you have to be very careful, because one is expanded to the gaseous state, it will take up the space and they will push away the breathable air you have. Okay, at the end, right, you might fainted. Yeah, so dealing with when you are handling liquid nitrogen, or when you are handling with the dry ice, please make sure that you are not in the confined space. Even you're talking about leaf is also confined space. That's why the other time when I was traveling on the leaf, when I saw them pushing the liquid nitrogen cylinder, is very big, taller than me, in the leaf, I straight away freak out and then I just leave the leaf here, because whenever you are transporting liquid nitrogen, you are not supposed to transport in the leaf with human, because if there is any leak of the liquid nitrogen onto the floor, okay, the liquid nitrogen will change to a gaseous state and it will push away all the breathable air and the person inside will faint. Yeah. death is possible as well. Okay, let's look at what affects the boiling point. Yeah, boiling point is affected by what we call the vapor pressure. Okay, whenever you heat, okay, whenever or another way is that whenever there's a temperature, okay, they will have a certain vapor pressure exists. Yeah, this vapor pressure is different from liquid to liquid. Okay, this vapor pressure is different from liquid to liquid. Yeah, so if when you're talking about water, the vapor pressure is at 20 degrees Celsius, or most room temperature is 17.5. Okay, so some of the molecules is will change to a gaseous state. Yeah, so it will evaporate slightly. Okay, so some of the water molecule escape from the liquid. Yeah, but very mild. Okay, at 20 degrees Celsius it's only 17.5 torr. Yeah, so the vapor pressure is very low. As the temperature increases, you can see from here you get higher and higher. Okay, boiling is when at 100 degrees Celsius. Okay, boiling is at 100 degrees Celsius at our atmospheric pressure. Yeah, 1 atm. Yeah, is because when the vapor pressure is more than the pressure, the atmospheric pressure, the pressure from the atmosphere. Yeah, okay, when it's more than that, it start to boil. Okay, that's why it's very important that atmospheric pressure for us when we are in the at the like for example where we are now, okay, in Taylor's Lakeside University, the pressure is 1 atm. Okay, 1 atmospheric pressure. Okay, or so what we are experiencing now is this. Yeah, if we go underwater when we are diving, go underneath the sea, okay, go under the sea, then the pressure will go higher. If we go to the mountain, the pressure will be lower. Yeah, okay, so that affects the boiling. So if you are trying to boil water in the mountain, when you're trying to boil water under the sea, the pressure is different. Yeah, the effect is different. For example, if you're trying to boil at Mount Everest, okay, on top of Mount Everest, the pressure is 0.329 atm. Yeah, what we in Lakeside campus or what we are in now is 1 atm. So in Mount Everest is a lot lower pressure. Okay, it's around about here. So what happened, right, is that when you try to boil, okay, when the water reaches about 70 degrees Celsius, around about that, yeah, 70 degrees Celsius, it starts to boil. Okay, it starts to boil because of the low pressure, because the vapor pressure, because of the vapor pressure reaches the same as the Mount Everest, the atmospheric pressure. Okay, and so it boils at 70 degrees Celsius. So when it boils at 70 degrees Celsius, what happened? You cannot really cook. Okay, because usually when we are cooking, we are boiling at 100 degrees Celsius so that you can cook your food. But when you are at Mount Everest, it boils at 70 degrees Celsius, so you can't really cook. Okay, because the temperature is not reaching enough. Alright. If you compare, if you want to like you want to suppress, okay, or don't want the water to boil that fast, you can actually use the pressure cooker. Pressure cooker is where it traps the steam in and increasing the pressure inside. When the pressure increases inside, what happens? Okay, when the pressure inside increases, you cannot boil because the pressure cannot just say that when the pressure cooker is reach about 1000 torr, so your temperature need to increase to about like 130, 140, only it start to boil. Okay, so what happened is that now instead of cooking at 100 degrees Celsius, you are cooking at 120 degrees Celsius or 130 degrees Celsius. Okay, with the increase in the temperature, what happened is that you can cook further. That is why the chicken you cook in the pressure cooker usually is more tender, because or it will melt. Okay, because you cook at a higher temperature. Yeah. Sublimation, okay, sublimation is when you change from a solid to a gaseous state. Sublimation is an endothermic process in which a solid is changed directly to a gas without first becoming a liquid. Okay, sublimation occurs under reduced pressure. Yeah, freeze drying is a technique used in the food industry and is based on sublimation. We remove the water from food material that is easily damaged by heat. So, other than the dry ice, you can also sublime. I guess the water can also undergo sublimation through a technique called freeze drying. So what happened, right, is that you freeze the water. Okay, the water can be in the food material, it can be from the vegetable, it can what. Okay, once the vegetable, just say, is frozen, okay, then you put the vegetables under vacuum. Okay, under vacuum, under reduced pressure, vacuum. So what happened, right, is that now the water, instead of going to liquid, it directly changed from a liquid from a solid state, which is ice state, into the gaseous state. Okay, so it actually evaporates. That's why you can see, right, freeze dry vegetables, okay, or freeze dry chips, right, you can see that if you open up, there are holes in there. Okay, it's because the water in there directly evaporated. Okay, not leach out, yeah, not, you didn't break it, yeah, it evaporated. That's why there's a lot of hole in there. Yeah, okay, so a change in state where heat is removed is called exothermic. Okay, if you are giving out heat, it's called exothermic. Okay, this one is what we call phase diagram. Yeah, each of the liquid, each type of the molecule or liquid, they have this kind of phase diagram. Okay, not only liquid. Yeah, each type of material, each type of molecule, they have their own phase diagram. This is a phase diagram of ice. Yeah, so if you really want to check, you can of solvent or whatever. Okay, find their phase diagram. Okay. For water, this is their phase diagram. So if you want to, at room temperature, yeah, so let's look at, so this is where we are, okay, experiencing currently at the moment, unless you're in mountain or under the seabed. Okay, so this is 1 atm. So at 1 atm, you can see from here, yeah, at 1 atm, if you increases the temperature, okay, if you increases the temperature from 0 to 100, yeah, so 0 is their still ice, okay, or below 0, yeah, is still ice. When you increase the temperature, it will change to water, and then it will change to above 100, it will change to gaseous, yeah, water vapor. But if you reduce the pressure, you can see, yeah, if you reduce the pressure, that's why under the vacuum, you can undergo sublimation. So after you become ice ready, then when you increase the temperature, that is where you use the freeze drying. Okay, but you will be asking, sir, so freeze drying you can dry everything, but it's very energy intensive because you need to create the vacuum first thing. Secondly is that you need to freeze it. Okay, freezing and creating at the vacuum and waiting for it to evaporate from ice to gaseous phase. It takes sometimes, depending on the material, sometimes it takes about like half a day, 1 day, 2 days, or 3 days. Yeah, so the product is very, very costly, but the final product is very, very high in quality because you actually evaporate at very low temperature. Okay, that's why NASA food, or what we call the space food, they use freeze drying. Okay, not the normal sun drying or air drying or heat drying and so forth. They usually use freeze drying to create the space, the astronauts' food here. Okay, how much heat is required to increase 1 degrees? You can is really based on the specific heat of a certain substance. Yeah, so the specific heat is very depending on the molecule. Is depending on the molecule. Yeah, what kind of molecule? For water, they have a certain set of specific heat. Yeah. So specific heat is equal to the heat absorbed divided the mass and the temperature change. So you can see from here, yeah, specific heat, or how we can describe, right, is that they absorb heat. Okay, they absorb heat. So you can see from here, if it's an empty paper cup, you put the fire, the paper cup will burn. But if you put water into the paper cup, okay, you try to burn it, you cannot burn it because the heat from the fire source is being absorbed by the water. Okay, it's by the water, so it is not available to burn the cup. It's very fortunate that the specific heat here for water is quite high. So you can see from here the specific heat. Water is liquid here is 1 calorie per grams here, so it's very, very high. So water absorbs a lot of heat, okay, per gram. If you compare to some others, okay, like here don't have here, so like what we call the alcohol, very, very low. Okay, so that's why we human bodies, okay, we use water to cool down our body, yeah, so that because of the specific heat is very, very high. Okay, last one, you can do some calculation, but it won't be tested. Okay, calculate the heat absorbed when 5 kg of water at 25 degrees Celsius heated up to 90 degrees Celsius. Heat absorbed equal to specific heat times mass times temperature change. So the specific heat of water is 1 calorie per grams per degree Celsius. This one is fixed already. Specific heat usually you can find from internet. Each material they have their own specific heat here. So you multiply by the mass, which is in gram, because the unit here is gram, and the temperature change is 25 to 90 degrees, so it's divided is 65. So in total, the heat absorbed from 25 degrees Celsius to 90 degrees Celsius is 325 kilocalories. That's a lot of calories here. Okay. Okay, so I will stop here. Please attempt the tutorial questions. Okay, so tutorial questions will be testing on you on unit conversion as well as calculation of the density. Yeah. Okay, so these two will be tested. Okay, so try to so please complete the tutorial questions. The tutorial questions, the answer is at the bottom as well. So try to attempt first before look at the answer. Yeah. So again, if you got questions, please ask in the Padlet. If you got no questions, please indicate you got no questions here in the Padlet, and that will be used to mark your attendance. Okay, so thank you very much. Okay.